Good morning, everybody. Sorry I couldn't be there today, but with technology, it's kind of nice. I'm never more than just a smart board away. First thing that we're going to do today is I want to have you all get your tests back from Unit 1. When you do get them back, I want you to page through them, make sure that the math is correct on all of them. And then also, if you've got any questions, I want you to make note of questions on the test that you can bring up to me on Tuesday, and we'll go ahead and answer those with the rest of the class. When you're done looking through those, take about 4 or 5 minutes to do so. We'll turn them face down, collect the tests, and then the sub can go ahead and pass out the progress reports for the end of Unit 1. So go ahead and pause the video now. All right. Next thing we want to do, I want to reference the second and last demo, I guess, that we did on Thursday, and that was taking the 2 test tubes, placing them in the hot water bath. The 2 test tubes had 2 different food coloring in them, one blue and one red. And we did see that there were 2 different effects. We had the red test tube, the liquid rose in that skinny tube, that skinny capillary tube, quite quickly. The blue liquid didn't rise as quickly as the red, but it did rise. So I know you had all drawn MLDs on your big whiteboards of this on Thursday, but it's been a while, so I want you to get with your partner again, get a large whiteboard, give me an MLD of the blue tube, an MLD of the red tube, and explain to me why both of these liquids are climbing that middle column. And then take a stab as to why you think the red one's going quicker than the blue. And Luke brought a good point up on Thursday. He said, well, the blue tube is not in the water as far as the red tube. So he suggested maybe the blue tube was colder. That's a great observation, but I'm going to say that's not the case. We're going to say that both the blue and the red liquid were at the same temperature. So I'm going to give you 5 minutes to draw. And then take about 3 or 4 minutes to go ahead and discuss this with everybody throughout the group. And then we'll come back to the video. So if the sub could go ahead and pause the video now. Alright, we'll go over the actual reason when we get into the notes. Alright, so the last demonstration, as you were all leaving class, you took a look at the diffusion tube that is still at the front of the classroom today. And as you look at it, it looks different today, or Monday, than it did on Thursday. You see a white substance in that tube. So again, I want you to draw an MLD. I want you to try to determine why that white substance formed. Remember, we had 2 cotton balls. Both of them were set into 2 liquids, 2 separate liquids. Those cotton balls were then inserted into the tube, and they were allowed to sit there for 20 minutes or so. So I want you to tell me why that white powder formed using an MLD. Try to figure that out. And then also, if you notice, it's that white powder hasn't formed right in the middle of the diffusion tube. It's more towards, I would say, your right as you're looking to it. Why? Try to figure out why that is. 5 minutes to draw. 3 or 4 minutes to discuss with each other. And let's pause the video now. Alright, so I'm hoping you had some good discussions, and hopefully you've gotten the points from those 3 demonstrations that I had done on Thursday. The red and blue food coloring in the 2 different types of water, the red and blue food coloring in the test tubes, and obviously the diffusion tube. And we'll clear up any inconsistencies you have with the following video, hopefully. Alright, today we're going to talk about heat and temperature. And to get to heat and temperature, we want to talk about a couple of obvious characteristic phase changes that you're probably familiar with from previous classes. So the term that's on the top of the page, evaporation. I'm sure you could all tell me what evaporation is. But we really want to know what it is on a molecular level. So I asked the following question. If you've ever had a fish bowl at home, why do we always have to refill a fish bowl? Why can't we just let the fish bowl sit there? And if you let that fishbowl sit there long enough, you're going to notice that the water level in that fishbowl is going to decrease. And your poor little fish is not going to have enough water to swim in. So every once in a while, you got to go ahead and you got to refill your fishbowl. There's my little fish. There he is. As liquid molecules, so we think about water. We don't want to think about it just as like one continuous substance. We want to think about all the individual liquid molecules. As these liquid molecules find the surface, they can actually pop out. So if you think about all the liquid molecules that are kind of located right here on the surface of our little fishbowl, every once in a while they get excited. And instead of staying in the liquid state, they get enough energy to pop out in the gaseous state. We can no longer see these molecules because we can't see individual molecules. The only time when you can see molecules is when they're together and when there's billions and billions of them together and with one another, as there are right there inside of the fishbowl. There's billions and billions and trillions and gazillions of molecules in there, and they're all tightly bound together, and so we can see the resultant substance, the liquid. But as soon as those molecules pop out of the fishbowl, we can no longer see that molecule. We can only make a model of that molecule. It's just way too small for us. The new state, the state of matter that we can't see, we call this a gas or a vapor. And the phase change here is known as evaporation. And you can notice the vapor and evaporation that are in there. So, what if we take that same fishbowl and we put it on your windowsill, and now it's in the sun? What's going to happen? Well, we're going to get a quicker rate of evaporation. And so we can now make this equality. We can say that molecules move faster. If they move quicker, then there's faster evaporation. Okay. So, let me go back, and let's talk about our diffusion tube. Here's our tube. And you notice that there's a white substance. I'm going to draw an orange because I can't draw white on white. Actually. Oh, gee. Beautiful. So our diffusion tube is there in purple. And here's our white substance that is formed in the tube. Right there. And we had one substance. Let's make it a red substance. Right here initially. And we had another substance, let's make it a green substance, over here initially. And what happened is both of those cotton balls that were absorbed in that liquid gained energy from the surroundings. So there was energy coming from here, and from here, and from here, and from here. And from here, and from here, and from here, and from here. And what we can say is the energy that was on the left side, so this energy, oops, sorry guys, let me go back. We can say that the energy that was on the left side, so this energy, was the same as the energy on this side. Why is that? Well, because both of these cotton balls were in the same room, and the room is at the same temperature. So the energy is the same. That energy transfers to the cotton ball transfers the energy to the liquid, and that speeds up the liquid molecules. And every once in a while, liquid molecules that are at the surface of the cotton ball pop out. And this is known as evaporation. And now we have little green molecules that are no longer in the liquid phase, but are now speeding towards the right. And we have other liquid molecules that are now speeding towards the left. And when they run into each other, they combine into what we know as a chemical reaction. And that's what you're seeing. You're seeing a chemical reaction. Now, you don't know names of chemicals right now, but this stuff is called hydrochloric acid. Same thing as stomach acid. This stuff over here is actually called ammonium hydroxide. And the stuff in the middle, the white material in the middle that you see, is called ammonium chloride, NH4Cl. And in there you can see that this guy is that guy, and that this guy is this guy, so it's a combination of the two. There you go, there's the diffusion tube. Alright, now, let's look at the opposite of evaporation. How can we prevent it? How could we make the evaporation not occur? We don't like filling up our fishbowl all the time. We could slow the molecules down, right? We know that cool molecules equal slow molecules. So we could take our fishbowl and we could put it in the refrigerator. Although that's a horrible idea because I don't think fish like refrigerators. Unless they're being frozen. And they don't like that either. Well, let's say, for instance, just for experiment's sake, though, we take the fishbowl and we do place it in the refrigerator and we let it sit there for a while. It's going to get cold. It's going to get pretty chilly. Well, now what happens when we take the fishbowl out? We get this stuff to form on the fishbowl. So we get air molecules, oxygen, nitrogen, carbon dioxide, water, that hit the bowl and they slow down. And especially water molecules. When they hit the bowl, they slow down pretty greatly. And these water molecules collect near the glass and they become more dense. And that's the middle term in our second term of the video, condensation. So condensation is nothing more than the molecules from the surroundings hitting something colder, slowing down, and then becoming more dense. That's condensation. We notice this every time we take a glass of water outside on a really, really hot day. We get condensation on the water. All right, two more things. Expansion and contraction before we get to heat and temperature. Let's say we take a balloon and we put it in a hot oven. So somebody made a turkey here with all the fixings for Thanksgiving out of balloons for some reason, and they've got it sitting in an oven. We want to know what happens to that balloon. Well, it would grow, right? It would get larger. We'd get from a small turkey, little baby turkey to a big tom turkey. But why would it grow? Why would it get large? Well, there's a relationship here that we have to understand. And that's that as the temperature of gases goes up, the speed of those molecules goes up. And the forces on the balloon go up. And so our balloons would grow and grow and grow until the latex that makes the balloon can no longer hold the gases, and the gases are too forceful, and they pop the balloon. And the rule is that hot molecules, they just take up more space. They take up much more space. We call this expansion. Expansion is just increasing the total volume that molecules take up. Now what if we take this same turkey and we place them outside in a Wisconsin winter? Well, the molecules are going to slow down naturally. And they'll take up less space. And we've noticed this for basketball players. We take the basketball outside in the winter. And we play for a couple of minutes, and then we set the basketball down, we go back inside, we get some hot cocoa, we come back out, and now the basketball doesn't bounce as well. That's because the molecules that are inside of the basketball have slowed down. They're not exerting as much force on the outside of the basketball, and we don't get as much bounce. This idea is contraction. Okay? This is just a decrease in the total molecular volume of a gas sample. Of any sample. It doesn't have to be a gas sample. Which brings me to my next slide. Can this happen with liquids and gases? Now I want you to think about that second demonstration. We had two test tubes, two skinny tubes in them, placing them in water. Think about the test tubes and the beakers and what happened. Well, we had liquid rise up that center column. So we have this red liquid rising up that center column. So the molecules that are making up the red liquid are moving faster and faster and faster. And when they do that, they spread out further and further and further, just like the gases in the balloon. Well, they can go two ways. They can go up inside the bottle, or they can go up inside the skinny tube. And there's a little property known as cohesion. And cohesion is that molecules, or liquid molecules, like to stick to things of large surface area. So when the liquid starts climbing up the tube, the liquid is more likely to climb up the skinny tube than it is the big tube being the bottle. So your liquid rises up the skinny tube. The hotter the liquid, the more it's going to expand in volume, and the more it's going to expand up that skinny tube. That explains the test tube demonstration. Now what I haven't explained is why did the red climb faster than the blue? And I still want you to think about that. What's an application of this? We'll take a look at a soda can or a soda bottle. There's always space at the top, right? This is for expansion. If you take a soda can and you place it outside on a very hot day, the water that makes up most of that soda is going to expand. And if the soda were full to the top, that soda can would burst. So that's why we always leave space at the top of the can. How about solids? Can solids expand and contract? Well, I ask you this. Why aren't sidewalks one continuous piece of concrete? It would be nice for rollerblading. Or, roller skating, I guess. It'd be super. You would never have to go over bumps. But you always have these little cracks in the sidewalk that look like they're meant to be there. And in fact, they are. These things are called control cuts. When Hannah's dad and his company goes out and pours concrete, they have to cut the concrete. They make control cuts. And the reason is because concrete itself expands and contracts. Right now in the winter, that concrete is really taking a beating with how cold it is. The expansion and contraction due to the water freezing and then thawing out is really wreaking havoc. But if you have good control cracks cut, then you don't have to worry about cracking that cement. So solid and liquid molecules also expand and contract. All right. So finally, 2 more slides. How can we use these ideas to measure molecular movement? Because that seems to be important when we're talking about how molecules move. I might ask this question. How can we tell how hot or cold something is? That seems kind of simple. We look on TV or on our phones, on the weather apps that we have on our phones. Well, let's think about this more scientifically, though. Let's say we didn't have an app or a TV or even tools to measure how hot or cold something was. We know this. When temperature increases, molecular speed increases. Okay? So our question might be, how can we measure this molecular speed? Molecules are too small. We can't use like a radar gun to say, how fast is it going? So we need some indirect method to be able to measure this molecular speed. Well, we know the following from previous slides. Faster molecules equal more hotness. We saw that with the balloons. The hotter the balloons are, the faster the molecules move, the more force they're pushing on with the balloon with. The more hotness, the more liquid expansion. And we saw that with the test tubes, right? The hotter the liquid was in the test tube, the higher it expanded. So we can make the assumption of that the faster the molecules are, the more liquid expansion there is. We can relate these two things, this guy and this guy. And we know that faster molecules equal higher temp. So at the end of the day, we can say this. The higher the liquid expansion, that must equal the higher the temperature. And in fact, that's what this dude came up with. His name was Andreas Celsius. And in 1742, he developed a little scale for understanding and trying to figure out how hot or cold something was. He knew that mercury expands an awful lot when heated. By the way, Hg is mercury. We'll get to that. So what he did is took a test tube, filled it with mercury, placed it in freezing water. And when the mercury stopped falling and shrinking and not shrinking, but contracting, he marked that level. And he decided to call that 0 degrees. He took that same test tube and put it in boiling water, and he marked that level. And he called that 100 degrees. Halfway between, he called that 50 degrees, and so on. Halfway between that, it was 25, and between that, it was 12.5, and between that was 6.25, etc., etc., etc. And thus, this was his new hotness meter. Well, Greek for hotness is thermos, and so it was his thermos meter, or as we call it, the thermometer. And this is how we now measure the temperature of an object, because we know that the heat an object has is related to its temperature. All right. Have a good one, everybody.